Hi everyone. So before we dive into today's topic, let me ask you something simple. Have you ever heard the phrase, too much of good thing can be harmful? Well, it turns out that applies not just to sugar or screen time, but even to things as solid and silent as metals. Yes, the same metals that build our homes, power our electronics, and even run through our blood in trace amounts can turn into silent threats when they cross certain limits. Can you imagine drinking water that looks clean but contains invisible traces of arsenic? Or working in a place where lead dust floats in the air without anyone realizing it? These are not just stories from textbooks, they are real challenges faced in both developed and developing countries. Today, we are going to explore how these metals behave in our environment and our bodies. So, everyone, welcome to today's session on an important and often underestimated topic in toxicology and environmental health, that is, the toxic effects of metals. Metals are all around us in the soil, air, water, the food we eat, and the products we use every day. Metals are naturally occurring elements found throughout the Earth's crust and are essential to various biological and industrial processes. Some metals play crucial or critical role in human physiology, while many others become toxic when present in excessive amounts. Their impact is not only limited to occupational settings or industrial environment, but also extends to public and ecological balance. Some have no biological role but are toxic at relatively low concentrations. Hence, the metal can be toxic when accumulated in the body beyond safe levels due to their persistence in the environment and bioaccumulative nature. Toxic metals are major concerns for the public health and environmental safety. In all of the sessions being conducted, we'll explore the history, challenges, movement of metal in environment, how and where the toxic metal enter our body, the mechanism by which they cause harms, specific health effects of various metals. Examples are lead, cadmium, arsenic, mercury. Real world examples of metal poisoning and contamination events. By end of all these sessions, you should have a clear understanding of why monitoring and controlling exposure to toxic metals is critical, not just in regulatory terms, but safeguarding human and environmental health. Let's look into the highlight for this session. Let's understand what is a metal, metal, how they behave as toxicants, movement of metals in the environment, routes of exposure and absorption of metals, distribution of metals in the body, metal transporters and metal binding proteins, excretion of metals. So here in this diagram, it is just an overview of metal toxicology. The diagram illustrates the toxicological pathway of metals or other environment contaminants from their origin to their adverse health effects on humans and ecosystems. So let's just see a breakdown of each component and how they are connected. So basically, their occurrence is in two forms, that is natural and anthropogenic. So in natural, metals can come from geological sources like soil, rocks and volcanic activities, while in anthropogenic, human activities like mining, industrial emissions and agriculture. From here, the metals enter two important paths, that is environmental cycling and chemistry. In the environmental cycling, this describes how metals move and change in the environment, the global distribution, the spread through air, water and soil, the biotransformation through microbial or chemical processes, the change metal forms. Then comes the biomagnification where the metals become more concentrated as they move up the food chain. This impacts the ecotoxicity, that is the soil, plants, wildlife, domestic animals, human exposure through food, air, water. Okay. In the chemistry part, this describes the chemical nature of metals influencing their behavior and toxicity. So in the chemical form, the speciation occur which where the different chemical forms of the same element can be seen. Then the essentiality, that some metals are essential in trace amounts. Then how the chemistry affects. It affects through the human exposure from determines how it is absorbed and used. Toxicokinetics, how it is processed into the body. Then comes the human exposure again, the pathways through which human come into contact with different kinds of metals. Then you have through occupational way, the environmental, dietary, medical. This leads to the toxicokinetics, where we look into how the body handles the metals through the dose, then the absorption, distribution, biotransformation, excretion. Then in turn, the host factors also impact on the toxicokinetics as well as the mechanism of action. So this also includes the individual differences affecting toxicity, that which comes are the age, gender, adaptive mechanisms, metal transporters, metal binding proteins. Then these factors influence the toxicokinetics and mechanism of actions. So how in the mechanisms we can look into how the metals are causing harm, like the advantageous binding and mimicry of biological molecules, oxidative stress, enzyme inhibition, DNA damage, gene expression or alterations. In turn, it gives out the adverse health effects. So final outcome due to all the above is the chronic diseases, developmental problems, neurological disorders, cancer, okay, etc. and many more. So in short, if we have to compile the things, it says that this flow chart here presents a comprehensive framework for understanding metal toxicity from source to effect, highlighting the interconnected processes between the environment, chemistry, human exposure, and biological responses. So let's start first by understanding what is a metal. So a scientific definition which states that a metal is an element or alloy characterized by a set of physical and chemical properties resulting from the nature of metallic bonding. So when you look into the periodic table, within a group there is often a gradual transition from non-metallic to metallic properties which are going from the lighter to heavier atoms. So some of the scientific properties of metals include the metallic bonding, electrical conductivity, thermal conductivity, luster, malleability and ductility, high melting and boiling points. So the metallic bonding, in metals, atoms release some of their outer electrons which become delocalized. These free moving electrons from a sea of electrons around a lattice of positively charged metal ions. This structure gives rise to too many of the characteristic properties of the metals. Next is the electrical conductivity. The delocalized electrons allow metals to conduct electricity efficiently, since electrons can move freely through the structures. Thermal conductivity. The movement of electrons and lattice vibrations, that is phonons, make metals excellent conductors of heat. Luster. Metal reflect light due to the oscillation of free electrons at the surface, making them appear shining or lustrous. Malleability and ductility. Because the metal bonds are non-directional, metal atoms can slide past each other without breaking the bond. This allows the metals to be malleable, that is hammered into thin sheets, and ductile, drawn into thin wires. The high melting and boiling point. Strong metallic bonds often results in high melting and boiling points, though this varies through element to element. Before starting with the toxic effects of the metals, we'll just look into the history. Humankind's use of metals has been critical to the progress and success of human civilization. Due to their very early use, metals are one of the oldest classes of toxicants known to humans. Eras of human development are defined by the development of specific metals such as the many copper alloys of Bronze Age and advancements in the Iron Age. The oldest documented environmental or occupational exposure to metals is that of the Tyrolean Neolithic mummy called as Earthsea, which is dated back to 3359 to 3105 BC, with copper and high arsenic enrichment in hair follicles. Human use of lead probably started prior to 2000 BC when abundant supplies were obtained from ores as a byproduct of smelting silver. Arsenical mercurial compounds have been used in Chinese medicines for thousands of years. The first description of abdominal colic in a man who extracted metals is credited to Hippocrates in 370 BC. Arsenic and mercury are discussed by Theophrastus of Urbis, that is 370 to 287 BC, and Pliny the Elder at 23 to 79. So here we'll also have some of the examples saying in the ancient times. One is about the lead, which was used by ancient Romans in pipes, cookware, cosmetics. Chronic exposure led to widespread of lead poisoning, possibly contributing to the decline of the Roman Empire. So some of the reasons which were stated was the mental decline, infertility. Next is the mercury, which was used in Chinese and Indian medicine as early as 1500 BC. It was also used by alchemists for chronic mercury exposure, led to neurological symptoms, which was also called as a Mad Hatter syndrome in 18th to 19th century hat makers. The arsenic, known as a poison of kings and used for assassination since antiquity, it was also used as a pigment and in medicine. During the Industrial Revolution between the 18th to 19th century, increased mining and metal use led to occupational exposures. Workers in smelting, paint, textile industries were often exposed to lead, mercury, cadmium, and arsenic, leading to systemic illnesses. Public health concerns started to emerge, but regulations were minimal. In the 20th century, cadmium linked to the Tai disease in Japan during the 1930s to 1950, caused by mining waste contaminating rice fields. Lead poisoning in children became a major concern due to the leaded gasoline and paint. Mercury poisoning, that is, examples are like the Minamata disease in Japan during the 1950s from industrial discharge in seafood. The toxic effects of aluminium were suspected in some neurological diseases, that is Alzheimer's, though this remains still a controversial subject. In the modern era, that is the 21st century, stricter regulations through EPA, WHO, OSHA now limit the exposure to heavy metals. Ongoing concerns with electronic waste, that is e-waste cycling, exposing workers to toxic metals. Contaminated water, that is Flint water crisis in the US, is an example. Use of nanometals and concerns about the long-term effect on the human health. Let's look into some of the challenges. Metal toxicology presents a unique and evolving set of challenges due to the diverse chemical nature, environmental persistence, and biological effects of metals. While some metals are essential for biological function at trace levels, many become toxic when exposure exceeds safe thresholds, or when individuals are exposed to combination of metals that act synergistically. Assessing and managing metal toxicity is complicated by several factors. The wide range of exposure sources, that is environmental, occupational, and dietary, the potential for bioaccumulation and long-term health effects, and the difficulty in detecting subclinical or delayed symptoms. Additionally, individual susceptibility varies based on genetics, age, nutritional status, and pre existing health conditions, further complicating risk assessment. From a regulatory standpoint, setting safe exposure limits is made difficult by the nonlinear dose response relationships of many metals and the lack of comprehensive data for newer or less studied elements. Treatment, likewise, is often limited to supportive care and chelation therapy, which may not fully reverse damage, especially in cases of chronic studies. These complexities demand an interdisciplinary approach combining toxicology, public health, environmental science, and policy to effectively address the health risks posed by the metals in the modern society. When you look into the metal toxicity, it presents several significant challenges for public health and environmental safety. Some metals like iron, zinc are essential in small amounts but become toxic at higher levels, complicating the establishment of safe limit, or you can say the safe exposure limits. Chronic low-level exposures such as to arsenic in drinking water can lead to delayed and non-specific symptoms, making detection difficult. Additionally, people are often exposed to multiple metals at once, which can interact in complex ways that amplify or reduce their toxic effects. Individual factors like age, genetics, and overall health also influence on how the metals behave or affect the body. Monitoring exposure is challenging as standard tests may not reflect long-term accumulation, especially for metals that are stored in the bones. Metals are persistent in the environment and can travel through air, water, and soil, making cleanup both costly and complex. The rapid rise in the use of emerging metals such as rare earth elements and nanometals has outpaced research on their long-term health effects. Furthermore, inconsistent regulation and weak enforcement, particularly in developing countries, contribute to ongoing exposure risks. Occupational settings also remain a concern as workers in industries like mining or manufacturing can still face harmful exposure despite existing safety regulations. Now, looking into the development and investigation of nanometal particles have uncovered a broad spectrum of previously unrecognized physiochemical behavior. At the nanoscale, metal exhibit unique characteristics such as increased surface area to volume ratios, enhanced catalytic properties, and size-dependent optical and electronic effects that deviate significantly from their bulk counterparts. These altered properties fundamentally influence how such nanoparticles interact with the biological systems. The surface chemistry of nanometals can be engineered for selective targeting, making them valuable in drug delivery, diagnostic imaging, and biosensing applications. However, these same interactions are also posing biological risks, which include the cytotoxicity, oxidative stress, and genotoxicity, which necessitates for careful evaluation. In short, the unrealized behaviors are at the nanoscale, metals can behave differently compared to their bulk counterparts due to quantum effect and increased surface to volume ratio. This also includes changes in their melting point, conductivity, and catalytic activities. Here we will look into how the metal behave as the toxicants. Here is just presented a scientific overview of the metal toxicity. The toxicological properties of a metal refers to how the metal affects biological systems, especially in the terms of toxicity exposures, metabolism, and health outcomes. In toxicology, when you look at the term metal typically refers to heavy metals and metalloids that can have toxic effects on the biological systems, particularly when these biological systems are exposed to chronic or high levels of the metals. These properties vary significantly between different metals and depend on several factors like the chemical form, the dose administered, the route of exposure, and the duration of exposure towards the metals. Metals can exert toxic effects on living organisms depending on their chemical form, the oxidation state, bioavailability, and route of exposure. These effects are governed by principles of toxicokinetics, which tells what the body does to the metal, and toxicodynamics, which tells what the metal does to the body. Here is a circular diagram which shows the toxic effects of metals. This diagram illustrates that heavy metal exposure can harm nearly every major body system from DNA and the nervous system to the skin and immune function. These effects can be interconnected, compounding the health risk of exposure, especially when multiple metals are involved. First, to start with, genotoxicity, damage to the genetic material, that is DNA, which can lead to mutations, cancer, or heritable genetic changes. Carcinogenicity, some heavy metals can cause or promote cancer by interfering with cellular processes or DNA repair mechanisms. Neurotoxicity, toxic effects on the nervous system, often causing cognitive impairment, memory loss, or developmental delays, example from lead or mercury. Reproductive and developmental toxicity, harmful effects on fertility, embryonic development, and offspring health. Metals like cadmium or arsenic can interfere with hormone function and fetal growth. Immunological toxicity, metals may suppress or overstimulate the immune system, increasing susceptibility to infections or autoimmune diseases. Skin toxicity, direct contact or accumulation of metals can cause skin irritation, allergies, or dermatitis. Cardiovascular toxicity, heavy metals can damage the heart and blood vessels, contributing to hypertension, arteriosclerosis, or other cardiovascular issues. Genotoxicity. This is repeated to emphasize the importance, again noted in the cycle, highlighting the central role of DNA damage in the toxic effects of metals. Toxicity arises from their ability to interfere with normal cellular processes by binding proteins and enzymes, generating reactive oxygen species, that is ROS, and disrupting essential biochemical pathways. Unlike many organic toxins, metals are not biodegradable and tend to bioaccumulate in organisms and biomagnify in the food chain, posing long-term risk to both human health and environment. Exposure to toxic metals can occur through inhalation, ingestion, or dermal contact, often in occupational settings, contaminated water or food, and environmental pollution. Depending on the type and level of exposure, toxic metals can affect various organ systems, including the nervous system, kidneys, liver, reproductive system, and may even cause cancer or developmental disorders. Understanding the toxic effects of metals is essential for developing appropriate safety measures, treatment strategies, and regulatory policies to minimize health hazards. This slide presented now is all about the challenges in assessing and managing the health risks of toxic metals around us. It outlines key issues that make it difficult to understand, regulate, and prevent the harmful effects of metal exposure on human health, including how metals behave in the body, that is, essential versus the toxic levels, long term, low level exposure risks, combined effects of multiple metals, differences in how individuals respond, limitations of current monitoring methods, environmental spread and persistence of metals, lack of research on new or emerging metals, gaps in regulation and enforcement, continued risk for workers exposed to metal on the job. In short, it is a summary of the complexities and limitations in toxicology, public health, and environmental safety related to metal exposures. The metal toxicity poses complex and multifaceted challenges to human health, environmental safety, and regulatory frameworks. One major issue is the complex dose response relationship of many metals. Elements like iron, zinc, and copper are essential for normal biological functions at low levels, but become toxic when their concentrations exceed certain thresholds. This dual nature makes it difficult to set clear, universally safe exposure limits, especially for vulnerable population. Another challenge is chronic low level exposure. Unlike acute poisoning, which produces immediate symptoms, long term exposure to small amounts of toxic metals, such as arsenic, lead, or cadmium, they can lead to several delayed health effects. These effects may be non-specific, such as fatigue, cognitive changes, or immune suppression, making them hard to detect and attribute directly to metal exposure. Mixture toxicity adds further complexity. People are rarely exposed to just one metal at a time. Multiple metals can interact in the body in additive, combined effects can be seen, synergistic, enhanced effect can be seen, or antagonistic, reduced effects in many different ways. These interactions complicate risk assessment and make it harder for health authorities to predict the outcome of real world exposures. Individual susceptibility is also a major concern. Factors such as genetics, age, nutrition, and pre existing health conditions can influence how a person responds to metal exposure. For example, children are significantly more vulnerable to the neurotoxic effects of lead, while individuals with poor nutrition may absorb more cadmium or mercury. Despite advances in science, biomonitoring limitations persist. Standard tests like blood, urine, or hair analysis may not accurately reflect total body burden or long term exposure. Some metals, like lead, can accumulate in bones and organs, remaining in the body for years and evading detection through routine testing. Environmentally, metals pose long term risks due to their persistence and mobility. Unlike organic pollutants, metals do not degrade. They can be transported through air, water, and soil, contaminating food chains and ecosystems. Cleaning up metal contaminated sites is often technically very difficult and extremely expensive, requiring advanced technologies and long term commitment. Compounding the issue is a lack of data on emerging metals. The use of rare earth metal elements, nanometals, and various industrial alloys has increased rapidly in modern technologies. Yet, toxicological research has not kept pace. As a result, the long term health effects of many of these substances remain poorly understood. Regulatory gaps further exacerbate the problem. Safety standards for metal exposure vary widely between countries and enforcement may be weak, especially in developing regions where industrial practices may still rely on outdated methods. This inconsistency results in unequal protection and continued high risk of exposure for certain populations. Finally, occupational exposure remains a significant concern. Workers in industries such as mining, smelting, electronics, and battery production, are at higher risk of metal toxicity. Even with existing regulations, the inadequate personal protective equipment, poor training, and weak enforcement can result in the harmful exposure that affect not only workers but potentially their families through take-home contamination. Addressing all the challenges of metal toxicity requires a multidisciplinary approach that includes improved research, stronger regulation, better monitoring tools, public health, education, and international cooperation. In this slide, we will look into the movement of metals in the environment. The movement of metals in the environment refers to the processes by which metals are transported, transformed, and redistributed across different environmental compartments, such as water, air, soil, and living organisms. The movement is influenced by both natural processes and human activities. First one is the sources of metal in the environment. Metals can be introduced into the environment through natural sources, that is, weathering of rocks, release metals into soil and water. Volcanic eruptions release metals like mercury, arsenic, forest fires, sea sprays. Anthropogenic, that is, human made sources by mining and smelting, industrial emissions, waste disposal and landfills, fertilizers and pesticides, automobile emissions, and e waste recycling. The environmental compartment and movement. First is the air. Metals like lead, cadmium, and mercury can become airborne through combustion or dust transported long distances by wind. Eventually deposited back to earth by precipitation that becomes the wet deposition or settling by dry deposition. Second is water. Metals enter water bodies via runoff, leaching from soil, industrial effluents, or atmospheric deposition. They can exist as dissolved ions like copper or zinc, like suspended particles in the form of complex with organic matter, transported through rivers, lakes, and groundwater. Soil. Metals accumulate in soil from atmospheric fallout, irrigation with contaminated water, or application of sludge. Binding to soil particles depends on the pH, organic matter content, cation exchange capacity. Metals can be immobilized or leached to groundwater. Next is the biota or the living organisms. Metals are taken up by animals and plants, sometimes leading to bioaccumulation and biomagnification in food chains. In bioaccumulation, there is a buildup in an organism over time. In biomagnification, increasing concentration up the food chain. The factors influencing metal mobility are the chemical form, that is speciation, determines solubility and toxicity. pH, acidic conditions increase metal solubility. Redox potential, it affects the form and mobility of metals. Presence of chelating agents or organic matter. Soil type and texture. Next is the environmental and health impacts. Toxicity to organisms. Metals like lead, mercury, arsenic, and cadmium can be highly toxic. Contamination of water supplies, soil fertility reduction, chronic exposure in human linked to neurological, renal, and reproductive issues. Then comes the management and mitigation process. The phytoremediation, which is done by using plants to extract or stabilize metals. Soil amendments by adding lime or organic matter to reduce metal mobility. The regulation and monitoring of industrial emissions and waste disposal. Cleaner production technologies. We have looked into the movement of the metals in the previous slide through a pictorial representation. In this slide, a brief summary is presented in a table for the various compartments. Let's start with air. So the sources are the industrial emissions, mining and combustion. The form of metals are in particulates and vapor form. Example is mercury. The movement or paths are through wind transport or deposition, that is wet and dry. And the key influencing factors are the particle size and the wind patterns. For water, the main sources are through runoff, leaching or through industrial effluents. They are found into the form of dissolved ions, complexes or particulates. The movement is through the flow in rivers or lakes or groundwater transport. The major key influencing factors are pH, redox and complexation. For soil, the source is through deposition, irrigation and fertilizers. They are absorbed to particles and precipitated forms. The movement is through leaching to groundwater and uptake by plants. The factors influencing are pH, organic matter and CECs. Next is the biota or the living organism. So the source is soil, water and air exposures. They are found into bioaccumulated forms and the movement or pathway is through uptake or food chain transfer, that is biomagnification. And the factors influencing are the species, metabolism and exposure time. In this slide, the diagram shows the movement of metals in the environment using a simple flow chart or flow chart structure. So it starts with atmosphere, that is the air, source of metals, the emissions from industrial activities or combustion. The arrow to soil and water, it indicates deposition metals from the air settle onto land and water surfaces via rain, that is a wet deposition, or dust, that is dry deposition. The soil, it receives metals from the atmosphere. Arrow to biota, this represents the runoff and leaching. Metals are carried from soil into water bodies when it rains or through groundwater movement. Water, it collects metals from both the atmosphere and soil. Arrow to biota, it shows uptake by aquatic organism which can absorb dissolved metals. Also possible, the metals settle into the sediments. Next is the biota or the living organisms. Metals accumulate in plants and animals. Bioaccumulation, the metals build up in an organism over time. Biomagnification, metals become more concentrated as they move up the food chain. Now let us look into the various routes of exposure and absorption of metals. Here presented is a table which will help us to make the understanding easier. Metals can enter the human body through several routes of exposure, and once inside, they can be absorbed and distributed to various organs and tissues. The main routes of exposure and mechanism of absorption of metals are as follows. So they are inhalation, ingestion, dermal and parenteral. So the inhalation, basically as we know it as a respiratory route, so the major exposure or source of exposure is by breathing in metal contains dust, fumes, vapors or aerosol. Common in occupational settings like welding, mining or smelting. The absorption can occur by when the metals can be absorbed through the alveoli in the lungs into the bloodstream. Factors like particle size, solubility and lung health affect absorption efficiency. The examples for this are lead fumes in battery plants, mercury vapor in thermometer manufacturing, cadmium oxide fumes during welding. So the factors affecting for inhalation are the particle size, solubility and respiratory health. The metals which are involved for the route of exposure in inhalation are majorly lead, cadmium, mercury in the form of vapor and arsenic. Next is the ingestion that we commonly call as a Oral route. So the mode of exposure is swallowing contaminated food, water or soil. Inhaled metal particles can also be swallowed through mucociliary clearance from the respiratory tract. So the absorption is metals are absorbed in the gastrointestinal tract, that is the GI tract, mainly the small intestine. Absorption depends on the metal's chemical form, nutritional status and age of the individual. Some of the examples are arsenic in contaminated drinking water, lead in paint chips or contaminated soil, common in children, methyl mercury in seafood. So the factors affecting the absorption are age, nutritional status, chemical form of the metal. The examples of metals which can be transported through the ingestion are arsenic, lead, methyl mercury and cadmium. Next is the dermal route or through the skin contact. So the skin contact with metal containing dust solutions or compounds. When they come into the contact with metal containing solutions, dusts or various forms of alloys, the absorption usually occurs through epidermis or it is limited. The skin acts as a barrier, so absorption is usually low, but certain metals or metal compounds can penetrate, especially if the skin is damaged. And the soluble compounds, that is organomercury, penetrates more easily. The factors affecting the absorption is integrity of the skin, solubility, presence of solvents or abrasions on the skin. Some of the examples are nickel in jewelry or coins causing allergic dermatitis, chromium in cement or tanneries leading to ulcers and sensitization, and the organic mercury. Next is the parenteral route. So the exposure can be by accidental or intentional, injection of metal containing substances, medical implant made of metal alloy can cause slow release of metals over time. So the absorption is direct entry into systemic circulation or tissues bypassing absorption barriers. So the factors affecting the absorption is dose, chemical form or site of administration. And the absorption site is direct into the bloodstream or the tissues. And the source of exposure is through injections or implants or leaching from metal-based medical implantations. The examples of the metals are gadolinium, cobalt and chromium. Gadolinium from contrast agents, cobalt or chromium released from joint replacements. In this slide, there are some examples which will help us to understand the metal toxicity more. So first is the arsenic. The route of entry for that is inhalation and ingestion. The health hazards related are cancer, irritation of respiratory system, liver and kidney damage, loss of appetite, nausea and vomiting. The permitted limit in ppm is 0.01. Next is copper. Inhalation and ingestion route of entry. The health hazard related are cancer and hazardous effects on aquatic animals. The permission level is 2 ppm. Lead. The route of entry is inhalation, ingestion and absorption through skin. Health hazards, brain damage, dysfunction of kidney, liver and central nervous system. Permitted limit is 0.01 ppm. Chromium, inhalation route, ingestion and absorption through skin. Hazards are lung damage and irritation of respiratory system. Permitted limit is 0.05 ppm. Cadmium, route of entry is inhalation or ingestion. Health hazard related are kidney damage, renal disorder, human carcinogen. Permitted level is 0.003 ppm. Metal, mercury, through inhalation, ingestion and absorption through skin. Health hazards are arthritis, kidney disease, damage in circulatory and nervous system. Permitted level is 0.006 ppm. Nickel, route of entry is inhalation. Health hazards are to lungs, liver and kidney damage. Permitted level is 0.07 ppm. Let's just take a moment to imagine something fascinating now. Every element, every metal we study embarks on a unique journey once it enters the human body. It's not just chemistry, it's storytelling at the molecular level. Some metals take the highway straight to the liver, others prefer the hidden paths to bones or the brains. Some behave like guests, supporting vital processes like oxygen, transport, or enzyme function, say iron and zinc, but others they sneak in like intruders, example cadmium, lead, and mercury, and settle where they don't belong, often silently causing the harms. Understanding how these metals are distributed, stored, and eliminated is not just a scientific curiosity. It's critical for protecting health, designing treatments, and shaping regulatory decisions. So, today, let's just dive into this microscopic roadmap of metal distribution. Let's not just learn about it, let's visualize it, change it, question it, because the more we understand their path, the better equipped we are to manage their impact, both good and bad. So let's start with the discussion for the distribution of metals in the body. So let's think what happens after metals enter the body. Metals, once they are absorbed into body, so say the various routes like inhalation, ingestion, skin contact or injection, they enter into the bloodstream and transported throughout the body are distributed to specific organs and tissues depending on the chemical nature. Some are essential metals like iron and zinc, as I told, while others are toxic like the lead and mercury. Metals usually travel in the body by binding to proteins like hemoglobin, albumin, transferrin, or metallothionein, or small molecules that help transport or store them safely. As with their actions at the molecular level, many non-essential toxic metals distribute and accumulate in the body by mimicking and competing with the essential metals of the similar physical characteristics. Metals disrupt metabolic functions by accumulating in organs or by displacing the vital nutrients or the metals. In this slide, let us look into how and where the metals are stored or accumulated. Let's start with lead. Lead is mainly stored in bone, that is, approximately 90% of the body's lead burden is stored in the bones. Lead is also found in blood and some soft tissues like brain, liver, and kidney. In blood, it binds to hemoglobin. Lead can cross the blood-brain barrier in children, causing neurological damage. Lead mobilized from the bone during pregnancy, exposing the fetus. Next is mercury. Distribution depends on the form, that is, elemental mercury vapor impacts the brain and the lungs. Methyl mercury can easily cross the blood-brain barrier and placenta, affecting the brain and fetal development. The inorganic mercury accumulates in the kidneys. Mercury, when binds to sulfhydryl group in proteins and glutathione, damages the cells. Next is arsenic. After absorption, distributes to liver, kidneys, skin, hair and nails. Arsenic has a high affinity for keratin, which is a protein in skin, hair and nails. It binds to sulfhydryl groups and is eliminated mainly through urine. Chronic exposures of arsenic affects the skin and can lead to cancer. Cadmium, it accumulates mostly in liver and kidneys, where it binds to metallothionein. It has an extremely long biological half-life, that is up to 3 years. Chronic exposure of cadmium can lead to kidney damage, osteoporosis, and lung disease. Next is chromium. Chromium is more toxic than chromium 3 and is more readily absorbed. It accumulates in blood, that is red blood cells, liver, lungs and kidneys. It binds to transferrin and albumin in the blood. Occupational exposure can lead to lung cancer and skin ulcers. Let's look into the next set of metals. Next is nickel. It accumulates in lungs, kidneys, liver and skin. It often causes allergic skin reactions, that is nickel dermatitis. It can enter via inhalation, that is through industrial fumes, or skin contact through jewelry. The main binding molecules of nickel are albumin, histidine and metallothionein. Next is iron. It is mostly found in blood as a part of hemoglobin and stored in the liver and bone marrow. Transported by transferrin and stored as ferritin or hemosiderin. Essential for oxygen transport and enzyme function. Imbalance of iron can cause anemia, deficiency or organ damage if found in excess. Let's look into zinc. It is stored in muscle, bone, skin and prostate. Zinc binds to metallothionein and enzymes. It is vital for immune function, wound healing and enzyme activity. Toxic only in very high doses. Deficiency can cause health issues. Copper. Copper accumulates in liver, brain, heart and kidneys. It is transported by ceruloplasmin in blood and stored by metallothionein. Essential for enzyme function and iron metabolism. Excess copper can damage the liver and brain. Example of excess copper is in Wilson disease. Next is manganese. Distributed to liver, bone, pancreas and brain. It enters the brain via olfactory nerve or bloodstream. Excess manganese can cause manganism or Parkinson like neurological disorders. Now, before we dive into the details further today, let's just look into something. How often do we stop and appreciate the silent guardians working within our cells? The ones who don't make headlines, but without whom the life itself would flatter. Yes, I'm talking about the unsung heroes, that is, the metal transporters and metal binding proteins, the ultimate gatekeepers and bodyguards of metal homeostasis. These are the proteins that decide who gets in, where they go, how long they stay, and when they must be escorted out. From ZRPs and ZNTs to ferritin, metallothionein, and transferrin. They work with precision and purpose. They manage essential metals like iron, copper, and zinc with the discipline of a military operation, while also helping to detoxify the harmful ones like cadmium or lead. They are the unsung decision makers, ensuring metals don't cause chaos, keeps balance, protecting vital organs, and even influencing gene expression and oxidative stress. So today, let's look beyond the elements themselves and focus on the brilliant system that controls them. Let's decide how these tiny molecular managers keep life in order and when things go wrong, how they may open doors to disease and toxicity. Here, it's not just about science, it's about control, defense, and resilience at a molecular level. And you're about to meet the team that makes it all possible. So, let's start with a discussion on metal transporters and metal binding proteins. The metal transporters are specialized membrane proteins that regulate the movement of metal ions across the biological membranes, that is, the cell membranes or organelle membranes. These metals are vital for various biological processes, but they must be tightly regulated due to potential toxicity. Metal binding proteins are a diverse group of proteins that can bind metal ions through specific chemical interactions. These metals are either stored, transported, detoxified, or used as essential cofactors for enzyme activity and structural ability. Why are these metal transporters important? So metal ions like iron, zinc, copper, manganese and other essential for enzyme activity, oxygen transport, DNA synthesis and repair, electron transport in mitochondria, immune defense and many more. However, too much or too little can disrupt this function. So precise control via metatransporters is critical. In this table, we will look into the main types of metal transporters. So let's start with the ZIP, that is ZRT and IRT like protein. So the mechanism which includes here is it imports metal into cytosol. So the primary metals which are transported are zinc, iron and manganese. The example of proteins are ZIP1 and ZIP4. The second is natural resistance associated macrophage protein, that is NRAM. It is proton coupled transport of divalent metals, that is iron and manganese. So it is basically in the immune cells. Next is divalent metal transporter 1. So here the mechanism includes proton dependent metal ion import. So primary metals which are transported are iron, manganese and cobalt. So it is the DMT1. Next is P-type and ATPases. ATP driven export or import. So is copper and zinc, that is ATP7A, ATP7B. In ABC transporters, the ATP powered import or export is the mechanism. Here, the iron is the primary metal which is transported through siderophores and zinc. The example proteins are the FAPC in bacteria and MNT-ABC. Next is the ferroportin. It is the iron export protein. The primary metal is iron as it is stated in the mechanism. An example of the protein is ferroportin SLC40A1 in humans. In this slide, let us look into few examples for diseases linked to metal transporter defects. The DMT1 leads to anemia due to defective iron absorption. The ATP7B causes the Wilson's disease due to copper accumulation in liver or brain. The ZIP4 leads to acrodermatitis enterophathia because of zinc deficiency and skin disorder. The ferroportin hemochromatosis due to iron overload disorder. Now, let us look into why are metal binding proteins important. The metals like iron, zinc, copper, manganese, cobalt and nickel are vital for enzymatic catalysis in DNA polymerase superoxide dismutase, structural roles, that is zinc fingers in transcription factors, electron transfer in cytochromes in mitochondria, oxygen transport and storage in hemoglobin and myoglobin. However, free metal ions are potentially toxic, so metal binding proteins are crucial for safe handling of these ions. Let us look into the functions of metal binding proteins. Storage. They safely store excess metals to prevent the toxicity. Transport. Moves metal ions through fluids or within the cells. Enzymatic activities. Metals serve as cofactors for enzymes enhancing their functions. Detoxification. Binds and neutralizes toxic heavy metals like cadmium and mercury. Metal sensing or regulation. They regulate the metal responsive gene expressions, that is, metalloregulatory proteins. The metal binding proteins play crucial roles in maintaining metal homeostasis, transport, storage, and detoxification in the body. These proteins selectively bind essential or toxic metals to control their biological availability and prevent cellular damage. Here are some of the most important ones which are presented in this table. Let's start with ferritin. The metal bound here is iron. The role is it safely stores iron within cells, especially in liver, spleen and bone marrow. It releases it when needed. It acts as a buffer against iron deficiency and overload. Transferrin. The metal bound here is iron. The role it plays is it transports iron in the bloodstream to various tissues, especially the bone marrow, for hemoglobin synthesis. It helps prevent free iron from generating harmful reactive oxygen species. Next is the metallothioneins. The metal bound is zinc, copper, cadmium, mercury, and lead. The role it plays is detoxification of heavy metals, regulation of zinc and copper homeostasis, protection against oxidative stress. A high cysteine content allows strong binding to metals via thiol, that is, the SH groups. Next is the hemoglobin. Metal bound is iron. The role it plays is it carries oxygen from lungs to tissues and returns carbon dioxide to the lungs. Each hemoglobin molecule contains 4 iron atoms in its heme group. The myoglobin, the bound metal, is iron. It stores oxygen in the muscles. Next is superoxide dismutase. The bound metals here are copper, zinc, or manganese. The function it plays is it neutralizes reactive oxygen species and it plays an important role in the antioxidant defense. Next is the zinc finger proteins. The metal bound is zinc. The function it plays is in DNA binding and gene regulation. Next are the cytochromes. The metal bound is iron in heme. It is involved in electron transport chain and cellular respiration. The cytochromes are essential for ATP production in mitochondria. There are some other proteins which also help in their roles. Okay, one is ceruloplasmin. The metal bound is copper. It majorly plays a role in carrying copper in the protein in blood. Also functions as peroxidase, converting iron to iron plus 3 for loading onto transferrin. It reduces levels are associated with Wilson's disease, that is copper overload. The other example is of albumin. The metals bound here are copper, zinc, calcium, which is loosely attached, and some other. It acts as a general metal transporter in plasma, also regulates osmotic pressure and transports hormones and drugs. It binds metals less specifically but plays a major role in the systematic distribution. Here we can just look into some diseases related to metal binding protein dysfunction. The tissue damage occurs from free iron due to iron overload, which is the hemochromatosis because of the ferritin. In the absence of transferrin, the impaired iron delivery to bone marrow occurs, which leads to iron deficiency or anemia. The failure to detoxify heavy metals, which is also called as a metal poisoning or neurodegeneration, occurs due to the absence of metallothioneins. The toxic buildup of misfolded proteins, which leads to amyotrophic lateral sclerosis, the ALS, because of the protein SOD1, which gets mutated. In this slide, we can just look into the summary or the features of metal transporters and metal binding proteins. The primary function of metal transporters is move metal ions across the membrane, while the metal binding proteins, they bind and regulate metal ions within the cell or body. The location is for metal transporters is the cell membrane, that is plasma or organelles. The metal binding proteins are found in cytoplasm, organelles, blood, extracellular space. The mechanism of action for metal transporters is ATP driven or passive transport. For metal binding proteins, it is they bind to metals via specific amino acid residues. Example for this is cysteine and histidine. The key roles which they play are for metal transporters, they import essential metals, export excess or toxic metals. The metal binding proteins, the storage, detoxification, transport within the cell, and enzyme cofactor. The examples for metal transporters are zip transporters, N-ramp, ABC transporters, P-type and ATPases. For metal binding proteins, ferritinin, metallothioneins, transferrin, superoxide dismutase. The target metals for metal transporters are iron, zinc, manganese, copper, nickel and cobalt. Metal binding proteins, same as whatever for the metal transporters. Additionally, the toxic metals like cadmium and mercury. The energy use, some require ATP, other use ion gradients. For metal binding proteins, generally no energy is used for binding. So involved in metal homeostasis? Yes, both metal transporters and metal binding proteins are involved. Pathological relevance for metal transporters is defects can lead to metal deficiency or overload disorders. For metal binding proteins, the abnormalities linked to oxidative stress or neurodegeneration occurs. Once the metals have played their roles, or if they are toxic, they must be removed from the body to maintain homeostasis and prevent toxicity. Excretion of metal occurs through several routes depending on the metal chemical nature, solubility and binding affinity. The excretion of metal refers to the physiological process through which the body eliminates both essential and non-essential metals after they are absorbed. Metal may be introduced into the body through diet, inhalation, dermal absorption or injection, like medical use or accidental exposure. Some metals are essential for biological functions like iron, zinc, copper, while others are toxic with no beneficial role, like lead, mercury, arsenic, cadmium. The body uses various mechanisms to regulate or eliminate these metals to prevent the toxicity and maintain homeostasis. We need to understand the metal excretion is crucial for toxicokinetics, monitoring exposure, designing detox therapies, compliance with the safety standards. In this slide, we will look for the main excretory pathways for metals. First one is the urine or renal route. The commonly excreted metals are arsenic, cadmium, chromium, inorganic mercury, uranium and zinc. The kidneys are the primary route for excreting water-soluble metals like zinc, copper and cadmium. Metals filtered by the glomeruli or secreted by renal tubules are eliminated via the urine route. Next is the hepatobiliary route or the feces. The commonly excreted metals are lead, copper, iron, organic mercury and barium. The liver can detoxify metals by binding them to proteins like metallothioneins and excreting them into biles. The metals like iron, copper and mercury are excreted through bile into the intestine and then eliminated in feces. This route is especially important for metals bound to bile or not easily filtered by the kidneys. Next is the gastrointestinal tract. The unabsorbed dietary metals are eliminated directly in feces. Metals excreted in bile also reaches the intestine for fecal excretion. Next is the sweat and saliva. Basically, the pathway includes the skin or the sweat glands. The commonly excreted metals are arsenic, cadmium, lead, mercury and nickel. Trace amounts of metals such as arsenic, lead and mercury can be excreted through sweat and saliva, though this is a minor route. Next is hair and nails. The commonly excreted metals are arsenic, mercury, lead used in biomonitoring. Slowly growing tissues like hair and nails can incorporate and retain metals like arsenic and mercury, providing a record for past exposure. They merely serve more as a storage or markers of exposure than primary excretory routes. The next pathway is for exhalation through lungs. This is basically for volatile metals. Commonly excreted metals are volatile compounds like elemental mercury or organic solvents. Metals such as elemental mercury vapor or arsine gas may be exhaled through the lungs. Here is a brief description for mechanism of metal excretion, that is filtration and secretion by kidneys. The metals circulating in the blood may be filtered by the glomeruli in the kidneys. Some metals are actively secreted into the urine using transport proteins. Kidney function is critical. If impaired, metal excretion declines, increasing toxicity risk. Next is binding to proteins. Metals often bind to proteins like albumin, transferrin, or metallothionein for transport and storage. These protein metal complexes may be taken up by the cells or excreted via bile or urine. Biliary excretion. The liver can modify some metals and secrete them into bile. Bile drains into the intestine where the metals are either eliminated in feces or reabsorbed. This is enterohepatic circulation. Let us now see some of the excretion pathways for metals. For lead, the main excretion route is through feces, bile, urine. The half-life of this is 10 to 30 years in bone. It binds to RBCs, accumulates in the bone. The mercury, it is released in the form of inorganic form in urine, feces organic, and lungs elemental. The half-life of mercury is weeks to decades. The methyl mercury crosses blood-brain barrier and placenta. Arsenic, it is excreted through urine. Half-life is 3 days. It is rapidly excreted, used for toxicity diagnosis. Cadmium, it is excreted through urine. Half-life is 10 to 30 years. It accumulates in kidney and the excretion is a slow process. Iron, it is very limitedly excreted out. There is no half-life for this. The excretion through sloughing of cells, menstruation, minor sweat loss. Zinc, feces in minor feces and urine. Half-life is hours to days. It is regulated based on the need. As we conclude today's sessions, we have seen how metals, both essential and toxic, interact with the body in intricate ways, from their entry and distribution to the precise handling by transporters and binding proteins, and finally the excretion. It's clear that the body has a remarkably sophisticated system to maintain balance and protect itself. Let us go through what we have seen in this session. We have understood what is a metal. This defines the metals based on physical and chemical properties like conductivity, malleability, luster, and distinguishes between essential and non-essential metals in biological systems. The behavior of metals as toxicants. The description about how certain metals like lead, mercury, arsenic can be toxic, causing cellular damage, enzyme disruption, or neurological effects. The movement of metals in the environment. Here we have seen how the metal travels through air, water, and soil, and how industrial, agriculture, and natural processes contribute to their distribution. The various routes of exposure, absorption of metals. Here outlines how metals enter the human body through various routes like inhalation, ingestion, or skin contact, and how they are absorbed into the bloodstream. The distribution of various metals in the body. We have seen how the metals are transported via blood, stored in tissues like liver and bones, and accumulate in organs affecting the functions. We have also seen the metal transporters and metal binding proteins. The highlights were the biological systems like metallothioneins and transport proteins that regulate metal uptake, distribution, and detoxification. And ultimately, the excretion of metals, which covers how metals are eliminated from the body via urine, feces, sweat, or bile, and factors that influence excretion rates. Understanding these pathways isn't just academic. It has real-world implications for toxicology, pharmacology, public health, and regulatory science. I hope that this session has sparked your curiosity and strengthened your grasp of how our bodies manage metals at the molecular level. Let's keep exploring in further sessions. We can also have questioning and connecting the dots because in science, every small detail leads to a bigger picture. Thank you all for your active participation. Let's carry out this knowledge forward into our practices and continue striving for excellence. Until then, this is Kanchan Mangale winding up this session. Thank you so much for your participation. Let's meet you into the next session. Thank you all. Thank you.